I think we'll get started. Our speakers here today are Roger Kjelgren and Larry Rupp. The tree water use and water stress response in the landscape, as well as forestry and fruit production, threads together Roger's research, outreach, and educational responsibilities. Roger has an undergraduate and master's degree in soil science and a PhD in forestry from the University of Washington. He has been a professor in landscape horticulture at USU since 2006. And we also have Larry Rupp joining us. He is a native to Taylorsville, Utah, and has been on the faculty at USU since 1984. He helped establish the Center for Water Efficient Landscaping at Utah State University and the Masters of Professional Studies in Horticulture program with its Water Efficient Landscape Management specialization. He also helped in adapting the Qualified Water Efficient Landscaper certification program for Utah. Larry and his wife Chris have 5 pretty good kids and 8 perfect grandkids, most of whom know how to pull weeds. So, with that introduction, I am going to bring up the PowerPoint and hand it over to our speakers.
Okay, I guess that's my cue to get started. I'm Larry Rupp, and let me just explain briefly how we want to be doing this. I'm going to do the first part, and then Roger will jump in as we get going along a little bit, and then I'll come back in toward the end, and we'll both be available and try and answer questions as they might come along. We do have quite a few slides, and we don't necessarily need to finish those, so please don't feel like you can't ask questions. We'd be more than happy to answer those, and that oftentimes is more helpful than the information that we might just come up with on our own. As we thought about what we might be able to present, I thought it'd be a good idea to just do a little brief overview of what's available and what the water situation is in Utah. And here's the crux of one of the situations we have with landscape irrigation. Of the culinary water, the drinking water, potable water we have available, figure about 65% of that is used for landscaping, and the other 35% is used for, of course, drinking and things like that. Now, this is a relatively small portion of water overall, since about 80% of the water that we have in the state is used for agriculture. But within the culinary water, landscaping kind of has a big target on it. And so if people are looking to save water, water districts, if they need to cut back, one of the first places they will look at is landscape irrigation. And that becomes a concern, of course, because not that we're not willing to conserve water, but that we don't want to see problems with damage or negative economic impact or things like that. If we look at the issue of why do we need to conserve water, I'm sure all are familiar with situation with water in the state, but just to go into a little more detail in Salt Lake County, and these figures are from the Jordan Valley Water Conservancy District, and what it shows is the water sources that they have and that they are predicting to use as they go into the future. And what you see here, this line is the demand for water if there is no conservation. And to meet that demand, they have various projects lined up, like using additional Utah lake water in the future. Bear River water is being looked at closely for being moved to the Wasatch Front. Additional water from Utah Lake and another project, and these are planned. These aren't in place, but these are things they're looking at down the road to try and meet that water demand. Additional water from mountain streams, and probably most scarily is this unknown source that will kick in somewhere around 2030. So they can predict this increased demand for water. If we can conserve water, then what we do is slow that demand or reduce that demand over time. So it gives us more time to be able to come up with new water sources or to create the infrastructure that's needed. Of course, the problem that we get into is that in any given year, there may be a wet year or a dry year, and that kind of creates the interesting dilemmas that we face in a water situation. Currently, as we look at the western states, we often feel like Utah is dry, and we are in somewhat of a drought. But as you can see on this slide, compared to California, we're actually in pretty good shape. Much of California is now in an exceptional drought. You've probably heard things on the news relative to that and the problems they're having with even simply getting enough irrigation water to be able to operate the farms in the Central Valley. So as we look at Utah, and we're anywhere from normal to a severe drought depending on where we are, it is a concern, and it is things that we need to be worrying about or be aware of, because as a result of these drought conditions, you may find yourself in a situation where you're being asked to either justify the water that you're using, or reduce the amount of water, or do some kind of conservation. So what we're hoping today is to, first of all, I'd like to give you maybe some justification, how you can justify the water that you need to use on trees, and then talk about some general landscaping practices that allow us to use our water as efficiently as possible. And then Roger's going to give you some specific ideas on how much water trees need and how to determine that. Okay, I don't see any questions yet. The other issue that we face when we look at water conservation is the concerns we're hearing with climate change. I don't think we need to get into the pros and cons of that, but there are some things that we need to be aware of. If indeed the climate gets warmer, what we're going to see is that there will probably be more rain and less snow in the mountains. If there's less snow, the snow actually acts as a reservoir on the mountains, and that means that we'll have less water stored for later on in the summer. If there's less snow and it's warmer, it will melt earlier. Again, that snowpack will be reduced and we have less overall storage. In addition, if temperatures are warmer, then we're going to have increased water use by trees. So as best as we can predict, water is going to be an issue in the future. I'm going to check my can everyone hear me out there? Am I talking in the...
It sounds like a few folks are having some trouble with the volume.
Okay.
If you are having trouble, well, I think it may be that the folks listening, if you need to adjust your speaker volume, either higher or softer, you can do that by clicking the little down arrow next to the speaker, and that might help adjust or make a difference there.
Okay, I'll try and speak louder too. Let me see if I can speak up. Okay, so the next thing I want to talk about was just a little bit on justification. It's easy to envision a scenario where someone says, "Why are we using water for trees? What's the benefit of that?" And there are several things. Some of them are quantifiable, some of them are not. And I just want to go through those real briefly. One of them, of course, is just aesthetics. Trees make our quality of life better. And sometimes that's hard to quantify or express, and I like this quote from Wallace Stegner when he talks about the first time he saw a lawn. Obviously, that's not a tree, but he talks about just how fantastic it was to see a managed landscape and what the beauty of that was. We know that trees can benefit our air quality. They can help with the problems we're having with increased carbon dioxide by sequestering that, also reduce pollutants. We can save energy through cooling, through shade and transpiration, help in the winter by blocking wind, and also in the summer reducing urban heat islands. Other things we can look at are runoff and erosion. Of course, having trees, plants in the landscape, we tend to intercept rain, reduce the impact, have reduced problems with runoff, and less soil erosion. In addition, it's well known that there are psychological and social benefits to having trees and landscape plants, and there's an economic value. Several studies have shown that if there are trees in the landscape, that improves the economic value of the property, and there's an economic value to the industry. Utah, for instance, has a multi-million-dollar industry that's tied into landscaping and the products that we have in the landscape. And at times that can be a problem. Years ago, for instance, former governor in the state, there was a drought, and he suggested that there be no landscaping, no new landscapes installed. Well, that may save water, but it has a huge negative impact on the industry. And so while we may need to save water, we'd like to be able to do that without negatively impacting the green industry. So if we look at how do we justify tree irrigation in time of drought, one of the problems is that, of course, we have a large economic investment in woody plants in a landscape that can't easily be replaced. If you look at the cost if trees die of removing and replacing dead trees, the cost of water versus the appraised value of trees, all those indicate that it would be a good investment to keep our trees healthy and alive. What we want to avoid is a situation like they had in this recent drought in Texas, and to their best estimates, they killed about 300 million rural trees and some 5 million urban trees. And that's a significant impact, both environmentally and economically, and something that we would hope to avoid. And if we can use a little water to do that, it's probably worthwhile. The interesting thing with trees is that they're not like turf grass. We often hear about turf in the landscape, and this is a slide of a home across the street from my place, and nobody was living there, and they kind of got behind on the irrigation, and you see the lawn in 3 stages there. Well watered where the sprinkler is, starting to get stressed behind the sprinkler, and totally dormant in front. It's interesting to note that this year I watched that lawn and it's completely green. There's not a problem with it. They didn't have to replant it or anything else, and so bluegrass will go dormant and recover. Of course, with trees we don't have that benefit. They won't necessarily go dormant, and we may lose the trees and the long-term investment that we've had in those woody plants as a result. I'd like to just go over a few things that we can do to make sure that we efficiently use the water that we're putting on in the landscape for our trees. First thing would be to control competition. Turf grass is competitive for water, weeds are competitive, and anything we can do to reduce that inappropriate water use, in the case of weeds, for instance, removing weeds so that the water is accessible by the trees. You see that slide on the left is a new planting at a park and ride in Cache Valley, and the weeds weren't controlled, and they actually ended up losing all of the trees that were planted there. increasing mulched areas around trees so that there's less competition with turf. All these things can help ensure that the water is used by the plants that we want to have use it. Another thing is to monitor the soil moisture status. Years ago, I was asked to look at some trees that had died, and went out and looked at them and noticed the soil was moist, but couldn't see many problems. So I put in a soil probe and found that it was moist or totally saturated for a couple of feet down. And then I went out a few days later and looked at it, and I saw the slide you see here on the left where the sprinklers had just shut off and the water that was puddling in that tree well. It turns out the problem here was that when they put in the sod, they had turned the irrigation up to get the sod established, and then nobody had remembered to come back and turn the irrigation down, and so they were literally killing the trees by overwatering. And the solution is just a simple matter of monitoring soil moisture status and seeing if indeed it is wet or dry. And that's an easy enough problem to have happen if somebody forgets to turn the water down. But after the trees die, if you get into situations like on the right hand here where you've got cattails growing where the trees used to be, that's a pretty good indication you're over irrigating, and maybe could cut back a little bit and be more efficient. Another problem with soil moisture status we see is kind of a question of what's going on underneath mulch. This is a slide of you can't really see it, but there's a dead shrub there toward the top, and again, a question as to why it was dying. Mulch looks dry on the surface, but when we pulled the mulch away, we found that there was standing water underneath. And again, speaks to the idea of actually getting out in the landscape and looking at it, seeing if it's wet or if it's dry. This is another example of that. This is a low water landscape in the Salt Lake area. You can see they've done a really good job of putting in gravel mulches and things, but there's obviously here in the center you can see the tree is under stress, and those shrubs, some of them have actually died. There's something going on there, whether it's a broken sprinkler or over irrigated or whatever it might be. There needs to be someone get out there and take a look at the soil and see what's going on. By the time it gets to this stage, there are pretty serious costs as far as having to go in and remove the mulch, remove the plants, bring in new plants, reinstall the mulch, and it can be quite costly. Other things we can do: avoid damaging root systems. This new construction was actually done quite well, but it kind of points to the idea that when we do go into construction, we need to be aware of tree roots and making sure that they're preserved as much as possible so that they can take advantage of the moisture that is available. I think another one might be encouraging the capture of natural precipitation. Sometimes we see landscapes with a lot of hardscaping that are designed to remove the water from the landscape. If we could get that water to the trees and plants instead of removing it, that would help us to be more efficient as well. I think another important point is that we need to be aware that if water's our most limiting factor or our most precious resource, then that ought to be the only limiting factor in the landscape. And we shouldn't be using plants that might be limited due to cold or insect or disease problems or lack of soil tolerance. So if we're going to invest the time and energy and water into establishing a tree, it would be in our best interest, I guess, to make sure that the tree is able to survive and isn't, after we put 10 years worth of water into it, that it isn't going to die during a hard winter. I think another big issue is looking at soil management, problems with compaction, the depth of soil. quality of soil that's used in construction sites, for instance, or where soil needs to be replaced. Just a couple of examples on that. Soil compaction can be a problem. People are often unaware of what can negative impact of heavy equipment on the soil, especially if the soil is moist. I think they're also very unaware of the problems that can occur to trees that are established if they're driving over that soil and compacting it, both as a problem for the roots of the tree, but also the soil's ability to hold moisture and make it available to the plants. This slide is probably as good an example as I can show you. If you look here at these lines going through this landscape, this was during a drought area. The irrigation was shut off, and you can see where portions of the lawn have gone dormant, and other portions remain green. And a fair number of those portions are where the trenching was done for the irrigation system. And what that indicates to me is that had all this soil, well, the compacted area of the soil is holding less moisture, it's less available, and had they taken the opportunity to break up that compaction before establishing the landscape, that it would have been able to hold more water and make that water more available to the plants. So soil it's hard to overemphasize how beneficial a good soil can be if it's not compacted, if it's not full of construction debris and things like that, and if it's appropriate depth. This is a little island in a box store parking lot. They removed all the topsoil, brought in road grade gravel, and packed that down, and then build a little planter box on top of it with about 6 inches of soil. And that makes it pretty hard to keep a tree as healthy and efficient as it should be. If we can get a little more soil depth, that can go a long way to helping out the situation. Okay, so we want to get a little bit into now specifically how much water do trees need, and just to kind of introduce that, with some plants we have a real good idea as to what they need. If you look at a sugar beet, it takes 230 kilograms of water to produce 1 kilogram of dry biomass. Corn's roughly the same thing. When we look at landscape plants like trees, we don't have values like that. And one of the reasons is that we don't have a concept of yield. We're not trying to produce X number of leaves or branches or wood. We do want to make sure that they're attractive and healthy, but that doesn't necessarily mean that they need to grow at a maximum rate. So we have a little bit of a different situation than we would trying to look at the water on a production agriculture situation. And this is kind of a good example of that. If you look at this slide, the arrow there is pointing to a Jeffrey pine, and over in the Reno area, and this pine was planted and was never irrigated. It was allowed to just grow under natural precipitation. And as you look at it, it's healthy, it's functioning fine, it's doing well. On the other side of the fence, though, there was trees that were planted at the same time that had been irrigated. And you can see the difference between a little bit of water for maintenance growth and enough water for maximum growth. So we can get huge differences and still have healthy functioning trees. And it makes things a little bit different as we're trying to figure out just exactly how much water is required than if we were trying to figure out how much water to put on our alfalfa. That being said, when we do low water or maintenance, we don't want to reduce it to the point where we're having damage or injury to the trees, but we can reduce it as part of our management situation. So with that, I'm going to turn it over to Roger. Roger, you there? Sounds like it.
I think so.
Yep.
Can you hear me? Okay. So we'll switch.
Little
Actually,
arrows
how do
on
I
the bottom
advance
left of
this?
those slides.
Okay, great. Okay. Okay, so I want to first switch gears a little bit from the tree back up to the environment that the trees are planting in. So any plant is going to respond to how much energy there is available to evaporate water, and that is driven by solar radiation. And I want to skip over to temperature, because temperature determines basically it's the size of the box that allows evaporation. The more temperature, the more potential there is to fill the air with water vapor. So the solar radiation creates the energy to evaporate water. Temperature determines the size of the box, and that can hold evaporated water. Humidity determines how much is already there. So the more humidity in the air, the less room there is for additional water to evaporate or transpire into that box. And wind determines how fast the evaporated water or transpired water moves into the box. So all four factors are closely integrated in determining evaporation and transpiration, because transpiration is simply evaporation from a leaf. But every plant does it differently, and because of that, it makes it difficult to have a standard approach. And ultimately, for a landscape, it requires knowledge, experience, and wisdom on the part of the landscape manager to make it work. So several reasons why understanding landscape water demand, how much is needed to irrigate landscapes and trees, is important. It drives the irrigation design. So the layout of the plants and the water requirements of plants guides irrigation. It also dictates and drives irrigation scheduling, when and how much. And you want to know the least amount, what's the amount needed to maintain the health, in this case trees, and not put on any more than you need, because one, you waste, and two, as Larry showed, for many trees, you put on too much water, you kill them. And if you don't put on enough water, they're stressed, they're not healthy, subject to insect or disease attack, and they may die. So another reason why it's very important to understand the water needs of the landscape in general, trees in particular, is that more water agencies across the west and the southeast are allocating a fixed amount of water, that end users get a certain number of gallons that they have to live with. And so it's a jigsaw puzzle. The landscape design has to estimate how much water is needed to fit in under the cap, under the allocated water. So a reasonable estimate, and I emphasize the word reasonable because there's no way for it to be perfect, but a reasonable estimate of water use of landscape plants in general and trees in particular can help managers live with the water allocation. And we have to look at this in the context of water demand, because water demand, as I mentioned, is evapotranspiration demand, how much water is lost due to evapotranspiration. It's a function of radiation, wind speed, air temperature, and humidity. And in the Intermountain West, I see there's people all the way from Washington State, where I grew up, and over to South Dakota. But we all see a curve somewhat like this, where you have rainfall in the west that's highest in the wintertime, or precipitation gets low during the summer and increases somewhat during the winter. Evapotranspiration, ET, goes up during the summer, so it's that gap between what evapotranspiration, the water demand, and the rain supplied is what we make up due to irrigation. And this happens to be water use in millions of gallons per day for Salt Lake City. You can see that water use, actual water use, tracks the ET rate very, very closely. And we measure, in the broad sense of the term, just about everybody who wants to find out how much water is needed, measures water demand in terms of evapotranspiration. And I want to be very careful here in terms of defining evapotranspiration as separate from, there are two flavors of it. There's what's actually being lost by the plant of interest, the landscape plant of interest, and then there's evapotranspiration defined as a reference that helps us compare among places and in between times. And for the across the West, the evapotranspiration rate, and let's just talk about reference right now, ranges from 0, meaning a cool, wet day, up to about 1/4 of an inch a day, meaning a hot day of maybe 90 degrees, 90 to 95, and a humidity of 10 to 20%. And we use reference ET as the standard for that. And reference ET is simply the water loss of a cool season grass that we define as a standard, and so that allows a comparison. And so keep in mind that when we talk about ET, it's always plant transpiration and soil evaporation. And reference ET, and it's always designated as ET with a subscript O, is again based on a hypothetical 4-inch high cool season turf grass. And again, it includes solar radiation, temperature, wind, and humidity. But the key thing about this is that reference ET is simply a hypothetical cool season turf grass. There's a lot of assumptions that go into it, and it's a very useful tool, but it's not a definitive tool because it doesn't tell you actually how much, and it doesn't even estimate how much is being lost from your tree or landscape plant of interest. But it is a useful framing tool. And it came to us by way of agriculture, where ETO for this cool season turf grass is fairly similar to the uniformity of a crop surface, where you have large fields of the same plant that is very smooth and very level. And so that allows for many simplifying assumptions. That's not the case with landscapes. So there's a multiplier effect or multiplier number that we use to multiply times the reference evapotranspiration to estimate, and this is only a rough estimation, of the actual water use of a plant. And research has come around to the number of 0.8 being a fairly reasonable number for turfgrass. Deciduous orchards can be from 0.5 for like a citrus up to 1 for an apples. So 100% of ET, grapes are 60 to 80%, and olives maybe a little bit lower. And so, but these are crop coefficients. And so it's a large uniform area where water use is closely linked to reference evapotranspiration. And so irrigation scheduling based on reference evapotranspiration is based on determining the evapotranspiration rate reference for your area of interest. It could be historical if you want a rough estimate, but real time if you want more precise. And then you multiply it times the crop coefficient, and that gives you the amount of water in inches needed to be replaced by irrigation. Okay, this works well, reasonably well for irrigated agriculture, although this number, the crop coefficient, is still, even in agriculture, highly variable. Okay, pretty clearly, landscapes are not the same as crops. Turf is kind of close, but something like a flower bed or trees, it's different because it's three-dimensional. So water loss is three-dimensional rather than two-dimensional from a uniform surface. And there's many different microclimates. So you may have a lot of shade that reduces water use under a tree, and full sun for this turfgrass, water use would be higher. So the urban environment or urban landscapes are characterized by complexity. It's highly complex in terms of water use because the three-dimensional structure is complex. The species diversity is complex, and that makes simplifying assumptions about water use more difficult. So do landscape plants have a crop coefficient? Well, first off, we can estimate plant water use in a landscape. We can have what we call a crop coefficient, but what do you do when again you have the diversity of several thousand different plants? Do you come up with a number for each plant species or variety? No, it's just not possible. It's too complex, and no one is going to pay me enough money to actually do it for every single plant, nor would I want to. So no, we cannot have a definite factor, crop coefficient for every species. So it's really important to understand, particularly for trees, that it gets even more complex, because for turf grass we can come up with a reasonable number. It's not perfect, but kind of close, because turf grass behaves like a free water surface in two-dimensional water use. But for trees, the complexity is three-dimensional water use. And so it's the whole the physics of water use of a three-dimensional tree is much more complex than a two-dimensional water surface or turf grass. And because we have so many different species, again, we can't do it for every species. So what we do is we group water use of basically trees and all woody plants into one, what we call a plant factor range. Now this is a complex chart, but I want to step through it. This is research done in here in Utah and also in Florida, where we measured water use. This is an example of it, of measuring water use of a sweet gum. So we actually measure how much by weighing the weight change of a tree. And then we calculate the depth of water use based on the amount of leaf area, and we divide that by the reference ET rate. And that comes up with what's the plant factor range here, ranging from 0, meaning that the plant's using 0% of water compared to reference ET, all the way up to 1. The take-home point here is that for these different species, green ash, plane tree, willow, maple, linden, mulberry, and sweet gum, is that water use on any given day will range by anywhere from 30 to 40%. It's highly variable. And even in different parts of the country, down here, water use of sweet gum in Utah, hot and dry climate with these black bars, and then in Texas, the white bars, is lower as a fraction of ET than it is in Florida. The reason for that is the arid zones have very dry air, and trees close their stomata, just like a circuit breaker in an electrical system will close if the current flow is too high. It's the same thing in trees. They shut down partially so they don't lose too much water, and basically, instead of burning up, they would actually pop their vessels and they would die. So what we've come up with is a plant factor that falls in this range of 50% for plants in arid climates. Higher in humid climates, but 50% of ET is a reasonable water use for rates in an arid climate, meaning from the Great Plains out to the West Coast. But that's not the entire picture. You have to look at trees in a landscape not only by the rate of water use, but also the number of leaves, the size of the transpiring leaf area. More leaves means more water use. This is a picture of a desert someplace in Utah. You can see where it's very dry, the plants aren't big, less leaf area, and they have very few leaves. So the plants themselves can tell you what they're adapted to and how much water they're using simply by the size of the leaf and the number of leaves. The bigger the leaf area, meaning a bigger tree, it's adapted to a higher rainfall environment. A small-leafed and small plant oftentimes has a much lower lower water use rate. And another way of looking at this is simply these are the mountains in Utah, but the same thing holds anywhere in the west that there's a mountainous region, and that at higher elevations, above 20 inches annual precipitation, large, dense canopy trees can be supported. But when we get down to 10 to 12 inches, there's not enough water to support trees, and it's incomplete plant cover. And when we get to deserts and 10 inches or less, not only the plant's small, but the plant cover is small. There's fewer plants per square yard, and so there's less total leaf area. So those are visible cues that help us interpret how to manage water for woody plants in the landscape. And this is a study we conducted at the Utah State University Botanical Garden with a lysimeter. That's simply a big pot in the ground that we measure the water coming out of. And this is 3 different types of landscapes. One using native drought-tolerant plants down here, and up here was using a conventional landscape. And what the take-home message here is that this plant factor, the water use rate as a percent of ET, increases with the plant cover, meaning that you have more plants, you have more water use. And that holds true for individual plants. That holds true for an entire landscape. If you have 100% plant cover, then you will have the maximum amount of water use. If you have incomplete plant cover, you reduce the amount of water used. So it's very complex dealing with landscapes, so we simply have to come up with very simplified assumptions and a more descriptive approach. And what the descriptive approach does is that it empowers you, the manager, so you can weigh in all these different complex factors based on your experience and knowledge and describe how they interrelate and come up with a reasonable, not a precise, because precise will be wrong. And precise is not the same as accurate. Precise measurements of water use in the landscape usually means that you're going to be wrong. A reasonable descriptive approach, you'll come up close enough to get a reasonable amount of water on the landscape. So currently, the Irrigation Association and the American Society for Agricultural Engineers is working on a standard for estimating landscape water use based on this approach, the simplified irrigation demand, where we make simplifying assumptions and come up with a common plant factor. And key in this standard is this idea that the leaf area matters a great deal, and that particularly if you're dealing with isolated trees, you need to look at the total leaf area, because that's telling you how much water this plant's going to need. And it is ultimately a descriptive approach. The numbers, ET rate, this plant factor, go into the description, and that helps you make a reasonable estimate. And they're not exactly prescriptive, because then you can simply overuse it and go very, very wrong. So how would this be applied? Simplified landscape irrigation demand and estimation. Cleverly entitled slide rules. Okay, so this is going to be part of the standard. So this minimum demand, a plant factor, is based on acceptable appearance. Many plants may have mild water deficits. That's okay. And this is actually used a great deal in fruit production, where they use water stress to control vegetative growth. Mild water stress usually is okay for most species. It's not okay when the species is so far out of its native habitat, like an aspen growing in a very hot and dry climate, that really no amount of water is going to make a difference. The plant is under stress anyway. So the basic assumption is that we have a plant factor, or a coefficient, but a plant factor is more accurate, is 0.5, unless there is evidence based on existing knowledge or a lot of experience for higher or lower value. So for an individual plant, we would use ET rate on a given time period, usually a week, times this 0.5. And if you want to know the total amount of water in gallons, you multiply it times the leaf area. And so how do you estimate leaf area? Again, this is another simplifying assumption. It's reasonable to assume that the leaf area is approximate to the cross-sectional area. This will not work for all species. For example, a columnar hornbeam or something like that, where clearly it's much, much taller than it is wide. So there are exceptions, but as a general rule of thumb, the cross-sectional area, or the radius squared, gives you the area of leaf that gives you a reasonable estimate of how much is being used. Now, having said that, in many cases, a sprinkler irrigation may be okay. And in that case, if you're just putting a depth of water down, there's no point in trying to estimate the actual volume. And so you would take simply the evapotranspiration rate times this plant factor, and this should be equals here. This is a ½ inch of water. And at a point based upon the average rooting depth of a given landscape, you replace that amount of water. And so the easiest approach here would simply be to say that once a week I'm going to put on 3/4 of an inch of water with the sprinkler system. And based on your knowledge and wisdom, we should not be to the point of severely stressing these plants. They may be mildly stressed, but that usually is okay. And it would be different than if you wanted to have the water use of a isolated tree. Let's say we had a crown of shrub that's 3 feet across, a tree 7 feet across, and this simply works through that we calculate the crown area, and then we multiply it times the plant factor, the ET, okay, 1.5 inches. And so 1.5 inches times 0.5 times 38 feet squared, and there should be a conversion factor of 0.623, gives you the gallons needed. And so this is just covering the surface of this process, but this gives you a reasonable approximation of how much water an individual tree is using. So again, this is just simply a restatement of the previous slide, that if you have, again, a tree of a certain size and you're going to be drip irrigating it, then you would want to know the gallons. And in this case, it would be 53 gallons. So it depends on how you're irrigating the plant. If you're irrigating it with a sprinkler, it's the same approach as turf grass. You're simply applying a depth of water. If you're drip irrigating it or applying water manually in terms of gallons, then you need the leaf area to estimate. And Larry, I think this is about where I turn over to you, I believe.
Roger,
Yeah.
we did have one question in the chat pod about figures and equations. Is there some place, we will record this session, so if anyone wants to go back and get those equations, you can always access this webinar, but are there some other places you can
point to information about this?
Exactly, a website or something that would have those.
There's the University of California. There's a colleague of ours named Dennis Pittenger who has developed a fair amount of information. So you'd have to go and do a search on him. His last name is Pittenger. We're working on a site here that will have. It will include an explanation of this process, the simplified process, and then it's a simple calculator. And it's really not a difficult calculation, but at least gets you a reasonable estimate of the volume of gallons needed by a tree or a shrub.
Thanks, Roger. I think rather than continue at this point, why don't we take some time and make sure if there's any questions we can get those answered. There's we have some additional slides. They talk about some things to watch for as far as water stress symptoms and some additional sources of information, but you could pick that up if you wanted to, looking at the PowerPoint after it's been put on the site. But at this point, are there any questions? Any questions for Roger? I think there's one here from Brent. Roger,
okay. Was this one text then? So the question is, could you explain the use of leaf area as a flat circle when trees have a 3D leaf area? Seems like leaf area should be calculated as a sphere. Yeah, good question. And I've been thinking about that for about 20 years now. If you think of a sphere, the sun is only striking half of a sphere. And even then, again, if you think of it as a sphere, the amount of radiation at the edge of it is not the same as being hit full on as a sphere. And if we've done the calculations, and here I want to acknowledge my colleague Richard Beeson in Florida, who has the most complete data set on water use of trees. And it worked out for about 80% of the trees and 80% of the situations that a flat circle, or as he called it, projected crown area, came within 10% of the actual water use of the tree. Once you start getting into a very conical tree form, then that starts to shift a little bit. Then the question becomes, how much is it an issue when you have such significant day-to-day variation? So the upshot is that, yes, a tree is a sphere, but only half of it is sunlit, and even of those sunlit leaves, many of them are not getting hit directly with solar radiation, so there isn't the energy to drive evaporation. Okay, so another question?
Yeah, it looks like Von Eisenman's asking if we have a chart that gives gallons needed based on ET and crown size.
Yeah, like we do. It's one that it's very. I have one that I've used in teaching. It's not posted online, but this is something Larry and I have been talking about, that we need to get this up. That yes, we don't have one immediately available, but yes, we will get one.
Okay, are there any other questions? If not, let me just hit a couple of more points here, if I could. One is that, again, to emphasize this idea that Roger said about descriptive, not prescriptive. Basically, what we're saying is that it requires professional judgment. And I always think of a statement Peter Lassig from Temple Square made, that the quality of the landscape is directly proportional to the amount of time it sees the shadow of the manager. And that's kind of true. If we're going to manage this water correctly, the manager has to be involved. You simply can't turn it over to a irrigation controller or some kind of mathematical formula that dictates how much water needs to be placed on it, because there are so many variables. So we want to reduce the risk of damage, and I'm sure this is the concern that most of you have is, okay, great, I'm saving water, but what happens if all of a sudden I've got trees that start dying, and how am I going to deal with that? And so the point is, I think, to try and reduce the risk by understanding the plant types, their adaptations, conditions, and whatnot, but still be able to save a little water while you're doing it. I wanted to just briefly touch on some ideas on water stress symptoms, because one of the things we can do is, as we're out in the landscape, if we observe stress, then we can act to respond to that. On an acute level, you might see things like wilt, You might see scorching of the leaves, especially if it's hot. Depending on the tree, there may be early leaf drop, or color may become a duller instead of a bright green. Evergreens, you might see needle discoloration, but for me, trying to determine if an evergreen, a pine or a spruce is under drought stress is really hard, because it seems like they're fine and then they're dead. So if anyone has ideas on that, I'd love to hear them. Anyway, chronic things, we end up with smaller shoots, shoot dieback, increased susceptibility to insects and diseases, which is a major problem, because we may not kill the plant due to lack of water, but we may make it so susceptible to other problems that it ends up dying anyway. So I think with that, I'm going to turn it back to Meredith so she can close this thing up before we run out of the hour.
Great. Well, thank you so much, gentlemen. I think this has been really informative. I've been getting some good comments just on the side about how helpful it's been. I think this is something we all struggle with. So I will close it up here. If anyone has any last-minute questions, it looks like there's a few folks typing in the chat pad, so we'll leave it open for another minute or so if you have anything you want to ask Roger or Larry before we close down here. Otherwise, I will pull up the polls that we had at the beginning, so please let us know. We always want to track who is signing into these into these webinars, so we can kind of gauge topics for the future. And I want to thank both of you, Larry and Roger, for participating with us today. We really appreciate your time and effort pulling this presentation together.
You're welcome.
Thank you, guys.